Our next presentation, Parametric Building Information Generation for Design and Construction. Ramon Heijden will be doing the presentation. Ramon, ready to go?
All right, sorry about the delay. Can you hear me in the back? Great. So thank you for joining this presentation. So my name is Ramon Heijden, and for the past 7 years, I've been working for Front. Front is a global facade consultancy firm that has a long-standing reputation for operating in all stages of the design and construction process. We would consult to architects in the early stages of design and would take that consultancy through all the way to contractors and even fabricators later on. And we take this approach throughout all stages of the process to ensure the highest level of quality that can be achieved on any job. So here are just a few examples of projects we have consulted on. Is this dropping out? It's dropping out, right? Yeah, that one is dropping out as well.
Got to hold it close to your mouth.
Okay, yeah. So let's just do two and see whichever one is working at. Thank you. Yeah. This is only a handful of examples of among the 200 build projects that Front has consulted on over the past 50 years. But in this presentation, I will present a novel way. The mics are just dropping out all the time. I'm going to just speak real loud. I will present a novel way of constructing large-scale and highly detailed BIM models. And this process is built around the principle of linking sets of information models by defining parametric and generative relationships between them. The result is a process that can be configured to generate any kind of output that may be required for a specific construction task. In this presentation, I will show a case study demonstrating how this process is applied to a real-world project. So the case study is the Morpheus Hotel in Macau, designed by Zaha Hadid Architects and commissioned by Melco Crown Entertainment. And Front's job was to design a facade system to cover the external structural steel that forms the exoskeleton. And our scope was limited to only the planning of the exoskeleton and only the complicated curved parts in the middle. And in this job, we were not consulting for the architect, but we were consulting for the facade contractor, who was then actually instructing the fabricator how to actually make these panels. And it was our job to prepare all the information that was necessary for the fabricator to actually use these panels. So our task was to analyze the design surface that was provided to us by the architect, design a framing system that would satisfy all geometric conditions, and perform structural analysis on the system in all its contexts, and ultimately provide fabrication documentation as well as assembly documentation for all parts and pieces of the entire system. So we designed a framing system that looks like this. A framing system that can accommodate all curvature, high wind loads, maintenance loads, and there was no welding constraint. No aluminum was to be welded on this job, so everything had to be mechanically fastened. So there were numerous mechanical connections that had to be documented as well. And all needs to be flexible enough to fit the existing steel structure design, which, as you've seen in the previous images, is not a very straightforward steel structure. But defining all these objects is just only one part of the job. In order to make it usable for the fabricator, it needs to be represented in many ways. And as is often the case with these kind of projects, the fabricator is not necessarily selected at the time the design and documentation process is started. So our process needs to be able to be flexible in creating all these different outputs. this is where I suppose the topic of this conference becomes of relevance. Because when dealing with complex geometry and high degrees of variation, like in this project, 3D modeling is the only option. And at this scale, and with this complexity, traditional BIM modeling is not a viable option. Therefore, we had to look for ways to automate the process. So Grasshopper, you may know, is a generative algorithm editor for rhinoceros. And Grasshopper is pretty good at processing complex geometry. However, when you have to deal with incredibly large models, like the ones we're talking about here, for example, there are over 1 billion moving parts in our scope alone. Scale. This is a Grasshopper definition that is pretty well organized. However, it is only creating one specific element type of the building facade. So when you have to create large and complex models, you typically need to create large and complex Grasshopper scripts. The larger the scripts, the more problems come with that. They will become increasingly hard to organize as elements and connections are getting in the way of one another. Zooming out starts to make the definition harder to navigate. It will take longer to process each step, and it can still only be operated by a single person. So when dealing with incredibly large models and equally large data sets, we need a way to dissect this process. The way Grasshopper does this is by compartmentalizing each function in a node. You have the user only deal with input and output. For instance, 1,700 lines of XML code are represented by only a handful of Grasshopper components. Each component has a clear task, and all the user cares about is the result of that task. Produced outputs can then be used as inputs to the next task. So in our process, we basically zoom out a step and consider a Grasshopper script to be a node in the graph. The outputs of the nodes are stored in a Rhino model, which can again be used as the input for the next Grasshopper definition. Now, why is it so important to distribute the model over many smaller models? Well, I will try to explain that. Each object can be represented in many different ways. Many trades need different representations and different aspects of an object. So for architectural renderings, for instance, you want the models to have the most detailed geometry possible. And materials as well as textures need to be assigned. But for basic indication of an object in space, you could do with a much lighter version of that model. And in order to determine, for instance, the sight lines from chairs, you only need to access the seating surface at the correct height. Some parties in the process just need to know properties of the object, such as dimensions. And for creating 2D drawings, you need another representation, and a quantity surveyor only needs to know how many. So storing all of these representations into a single model creates an unnecessarily large and heavy model that is very hard to operate. And by definition, it means that everyone making use of this model needs to deal with way too much information and way too large models. So in our process, each representation of an object is stored in a separate model that is coordinated from a lower level model. And they're basically all connected together through means of Grasshopper definitions. So the concept of algorithmically linking all models to one another makes for more flexible model updates. And this image explains the value of algorithmically driven processes as opposed to a manual approach. Simply adding a bunch of seats while maintaining all constraints of accessibility, seat rotation, and sight lines would completely disrupt the seating layout and would basically require remodeling the entire arrangement. But with algorithmically driven modeling, these changes can be made in a matter of minutes. So how does this work? The way we access the geometry in Rhino models is by querying the geometry attributes. We basically call in geometry from the Rhino model by specific attributes. This way we create a text-based binding that does not rely on the actual object. And by saying that, I mean that the original object can be replaced at any time, but as long as the attributes are assigned consistently, the new object will be recognized and processed accordingly. So Front has developed a plugin called Elefront for this task. And the plugin allows users to assign these attributes to the Rhino geometry when baking from Grasshopper, as well as referencing the geometry back into Grasshopper from Rhino. So here we see our Rhino viewport showing one of the panels in the project. The property panel to the right shows all of the attributes assigned to a single part. So this part, for instance, will at any time have a bunch of attributes assigned to it. And these attributes are typically inherited from parent objects and complemented with some specific attributes that are specific to this part. So from one stage to the next, all attributes from the input objects are preserved, combined, and complemented into the next stage. As the output is generated automatically, so is the information. And therefore we call this process building information generation. And the result is a network of models that each contain information about a specific part at a specific point in the process of the model generation. We call this a distributed data model. It consists of discrete sets of data that are stored in Rhino files and represented as attributed geometry. Each Grasshopper file in the network typically creates one type of object, and more specifically, one version of that object. As I will show later, it typically takes a few modeling steps to get to a specific representation of an object. And by separating these steps out into individual models, anyone at any time can have access to each step of the generation process for each type of object in that model. Each task requires specific inputs to be able to generate the output. And these inputs now can be mixed and matched from a myriad of models that all contain coordinated information. Using this principle, you can easily scale up your project with the only limitation currently being disk space. Another huge benefit of this approach is the fact that each node in the model can be operated by a different person. It is now possible to collaborate on a Grasshopper-driven 3D modeling process with a large number of people and trades. As long as the attributes are assigned consistently and the Grasshopper scripts are robust, changes can be propagated without too much disruption to the project. Now, in the design and construction industry, collaboration and data exchange between different trades and software has always been problematic. In most cases, it is possible to convert geometry from one platform to another, but most of the time this means that any other data about the object is lost. With building information generation, all objects are represented by some form of geometry and a large set of data. The instant accessibility of this data makes for flexible reformatting of the data. And so we are now able to communicate with different software platforms on a much lower level than with model file exchange. But now that we know the specifics, I will try to illustrate the entire workflow with an example creating one part of this panel. So let's pick one element of a panel and follow it all the way through this process. In this case, we'll be following the creation of a stiffener element, which is a pretty basic part of the framing system. The initial inputs we need for this process are the panel surfaces that we derive from the architect's model directly. The mean planes, also created by the architect, and the steel connections that we had modeled in a previous stage, and the structural steel connections that penetrate through our panels at unpredictable locations. And this model, the steel model, was produced by the structural consultant. And the panel surfaces determined where the stiffener should go. The mean planes determine how the stiffener should be aligned. And the steel connections and the stub penetrations restrict the placement options of these stiffeners. But the final model should look like this. The ideal positions for the stiffeners are determined by a set of rules. And these rules are dictated by systematical constraints, practical considerations, as well as structural requirements. The real-world constraints are translated into grasshopper definition that determines the typical location for all stiffeners. The steel connections and the stub penetrations create zones where stiffeners cannot exist, the so-called no stiffener zones.